Hello everyone, this is part 3 of using Laplace transforms to solve initial value problems. So this will be a short video, just have one problem to solve, number 4 here. But we saw in number 2 and number 3 how we needed to use partial fraction decomposition because our table is constructed such, the Laplace transforms are such that you can only have either linear or irreducible quadratics in the denominator. So we'll see another example here. So start as normal. Remember, you want to use the linearity property and change these over to functional notation as well. So the Laplace of x double prime of t plus 4 times the Laplace of x of t is the Laplace of cosine of t. So we got a non-homogeneous here. Okay, so x double prime of t, its Laplace is s squared uppercase x of s minus s lowercase x of 0 minus lowercase x prime of 0. And then we have plus 4 times Laplace of x of t is uppercase x of s. And then for the Laplace of cosine of t, unless you've memorized them, go to your table. And cosine of kt is s over s squared plus k squared. So cosine of t, that's 1t, so k is 1. So we'd have s over s squared plus 1 squared, or just simply s over s squared plus 1. Okay, so now immediately remember you always want to substitute in the initial conditions after you Laplacize. And so we have s squared uppercase x of s minus, okay, x of 0 is 0. Oh, so that's 0. Not even write that. And x prime of 0 is 0. Making it a little bit simpler. Yeah. I'll show it anyway. So you gotta show an extra step. So minus s times 0 minus 0 plus 4x of s is the s over s squared plus 1. Okay, so now let's factor out the x of s from the left. Nothing to transpose. So factoring out uppercase x of s, we have that times s squared plus 4. And that's equal to the s over s squared plus 1. And then dividing by s squared plus 4 is really the same as multiplying by 1 over s squared plus 4. So basically it just drops down into the denominator of this fraction on the left-hand side. So we'll have s over s squared plus 1 now joined by the s squared plus 4. Because you could either think of dividing by it or multiplying by 1 over s squared plus 4, and that's what we get. Okay, so there's the product of two factors. Can't deal with products, remember, to go to the inverse Laplace. So we got to go to partial fractions, and go up here, and the partial fraction decomposition is going to be such that s over s squared plus 1 times s squared plus 4 is equal to, okay, notice that they are both in the denominator. We have two irreducible quadratic factors, and so we can't factor those because it's the sum of two squares. So we're going to have two fractions, one with s squared plus 1 and one with s squared plus 4. But if you recall the method of partial fractions, the only reason we were able to put just constants above each of these in the last example was because these were linear factors in the denominator. So the only thing that could go above them to keep them proper would be constants, because I couldn't put an s up there because it would no longer be a proper fraction. But when we're dealing with irreducible quadratics, you should recall from Calculus 2 that to account for all possibilities that would keep the fraction proper, we need a linear factor and a constant term. So we'll say as plus b, and consequently cs plus d. So that certainly is important to recall. Okay, now the working equation. So we're multiplying by the least common denominator, which is the denominator on the left. So on the left, we just get the numerator s. If we multiply as plus b over s squared plus 1 by this denominator, the s squared plus 1's cancel. So we get as plus b, imperative to use parentheses around that, times the binomial s squared plus 4, and similarly plus, again, important to use parentheses around the cs plus d, and that times s squared plus 1, because the s squared plus 4's cancel. Alright, now, because they're irreducible quadratics, there is no convenient way to choose just constants to solve for the terms a, b, c, and d. And so you might recall that what we have to do, well, you could use the imaginary unit if you wanted to. That's one way to go about it. But I'm going to use the comparison method. So I'm going to start by comparing powers of s, beginning with the highest power of s in the working equation. And if you imagine distributing and foiling each of these out, you'd get s cubed. So I'm going to compare the s cubes. On the left, there are 0 s cubed. On the right, there is an as cubed, coming from the product of as times s squared. And there's a cs cubed, coming from the product of cs times s squared. So that gives, when we divide out the s cubes, 0 equals a plus c. So there's one equation and two unknowns. Okay, I'm going to continue and I'm going to compare the s squareds now. Okay, I got to try to squeeze this in because I didn't give myself enough room. So I'm not going to write the word compare. I'll just do this. I'll say s squared. I'm going to compare those. Okay, on the left-hand side, again, we have 0 s squared. On the right-hand side, if you imagine foiling this out, we get a bs squared. But that's it, because a is times s, as times s squared is as cubed, and as times 4 is 4as. So that's all there, and then similarly plus a ds squared. C is not associated with an s squared. So we get 0 equals b plus d. So there's another equation, but two different unknowns. Alright, so let's go down and compare the s's. If we take the product of as times 4, okay, on the left we have 1s. On the right, as times 4 is 4as. And then plus cs times 1 is plus 1cs. And so then dividing out the s's, we get 1 equals 4a plus c. There's another equation, same two unknowns as the one above it, so we'll be able to solve that system. And then finally comparing the s's, or excuse me, comparing the reals, or the constant terms. We have b times 4, which is 4b, equaling I'm sorry, on the left, what do we have? There's no constants on the left with the working equation, so 0 equals on the right. We've got b times 4 or 4b, and then plus d times 1 or d. Okay, so now we'll solve the systems. Here, let me keep this line separated because we've got them lined up neatly. So 0 equals a plus c, 1 equals 4a plus c. I'm going to multiply the top by -1. Solve the system any way you want. Whoops. I'm sorry, you couldn't see the last few things that I was doing. I'll give you a second to catch up there. So when I was comparing the s's, they had as times 4 to get 4as, and there was no other s's involved there. And then similarly here, cs times 1 gives us cs, and there was one s on the left hand side. And then dividing out the s's, we got that. Then comparing the reals, b times 4, 4b on the right, d times 1, 1d, and there's no constants on the left, so that's it. Alright, so then the systems line up the two equations, multiply the top by -1, you get 1 equals 3a, so then a is 1/3, and back substituting, zero equals a plus c, so 0 equals 1/3 plus c, so c is -1/3. Okay, and then for this system, line them up again. I'm just doing the algebraic method. And again, I'm going to multiply the top by -1. And we get 0 equals 3b. So then b is 0. And back substituting, 0 equals b plus d. But b is 0. So d is 0 as well. Okay, so now back up to x of s. In terms of the partial fraction decomposition, as plus b, a was positive 1/3, so 1/3 s over s squared plus 1, because b is 0, so no need to write it. And then plus cs plus d, c was -1/3, d is 0, so -1/3 s over s squared plus 4. Okay, so now we're ready for the inverse Laplace to find x of t. So lowercase x of t, inverse Laplace of what we just found, uppercase x of s, that is. To use the linearity property, so we get 1/3 inverse Laplace s over s squared plus 1, and then minus 1/3 inverse Laplace s over s squared plus 4. And so finally, to our table, we have, okay, it's s squared plus k squared, which is cosine of kt with an s in the numerator, and that fits each of these. First one where k is 1, so x of t is 1/3 cosine of 1t, or just simply cosine of t. And then this fits the form where k is 2, and so 1/3 of cosine of 2t. Okay, so that's it for this topic, and next time we'll see how to solve systems of differential equations.